let's convert, let's go through a few examples where we're looking at exponentials. Now here, log of a plus 2 ln of a plus 2 ln of b minus ln of c. We want to turn this into a single log. So ln of a plus 2 ln of b minus ln of c. Now, to help with this, I'm going to put some brackets in. Because remember, order of operations is left to right, but here, putting these brackets in actually helps with the computation because we don't get confused. So here, we can bring this 2 up. So it gives us ln of a plus ln of b squared, all minus ln of c. Well, this equals ln of ab squared minus ln of c, which now I can divide to give me ln of ab squared over c. One nice logarithm. Well, now we have this expression and we want to solve for x. So we want to get x by itself. Now I have x's in the exponents. How do I get x's out of the exponents? We apply ln to get our variable out of the exponent. Okay. So I'm going to take ln of e to the x plus 2 equals ln of 4e to the x 2x. Now here, before I can bring it out, these two numbers are multiplied. I have to separate that multiplication before I can bring the next exponent down. So let's go through how we would do that. Here, this becomes x plus 2 times ln of e. And this becomes ln of 4 plus ln of e to the 2x, which implies that x plus 2 times ln of e equals ln of 4 plus 2x times ln of e. Now, ln of e is equal to 1. So this implies that x plus 2 equals ln of 4 plus 2x, which implies that 2 minus ln of 4 equals 2x minus x, which implies that x equals 2 minus ln 4. For the final expression, what we're going to do is we're going to determine the domain of this function. Well, there's 2 possible domain restrictions. We have square root x e to the x plus 1 equals 0. And we have e to the x plus 1 is greater than or equal to 0. This is from 1 over g of x, and this is square root of g of x. Now, here, we don't want to equal 0, and here we want to be strictly greater. Now, this implies, by squaring both sides, that e to the x plus 1 does not equal 0. And this is true for all x. Here, this implies that e to the x plus 1 is greater than or equal to 0. And this is also true for all x. And we can look at it by looking at the function e to the x, which is here. And we're going to move it up 1. So that gives us the function e to the x plus 1, which never equals 0. For suggested exercises, I encourage you to work through these. Solve the following inequalities. You got some absolute values, you got some strictly less thans, we've got different bases. I highly, highly, highly encourage you to work through these, as it'll give you lots of practice using your ln. Now, we had mentioned that the ln function was the inverse function of the exponentials. So let's just talk about inverse functions in general. Okay? An inverse function is a function that undoes another function. Suppose g is the inverse function of f of x. Then g of f of x, if f of x equals y, f of x equals y if and only if g of y equals x for all x in the domain. So this is true for all x in our domain. If a function has an inverse, the function is called invertible. We use f to the minus 1 of x to denote the inverse of a function. Remember that the inverse is different than the reciprocal, or 1 over f. This here, this is my reciprocal. Let A be the domain of f and B the range of f, as f of x, we're just going to wait for this screen, as f of x equals y, if and only if f inverse of y equals x, we get the cancellations formulas. F inverse of f of x equals x for all x in A, and f of f inverse of x equals x for all x in B. It is important to know that not every function has an inverse. For example, f of x equals x squared and f of x equals sine of x do not have inverse. We will discuss these functions in more great detail shortly. For now, we'd like to know when a function does have an inverse. When does a function have an inverse? A function f of x has an inverse when f of x never takes the same value twice. A function with this property is called 1, 2, 1. A function is called 1, 2, 1 if it never takes on the same value twice. That is, f of x1 does not equal f of x2 whenever x1 does not equal x2. Now, the horizontal line test is a great way to test to see if a function has an inverse. Remember when we looked at functions and we had the vertical line test, which told us whether or not it was a function. Now we have a test that tells us whether or not it's an invertible function or a function has an inverse. And here we're going to do horizontal lines. And if the horizontal line only touches once, then the function, and it passes the vertical line test, of course, then the function has an inverse. A function is 1, 2, 1 if and only if it has no horizontal line intersects the graph at more than once. So if we look at these different graphs, here we touch 1, 2, 3. Oh, it's more than once. No. But here, no matter where we touch only once. So this is 1 to 1. Here, I touch twice. This is not 1 to 1. And then here, I touch once. So here, we have 1 to 1 functions, which are invertible, and functions that are not 1 to 1, which don't have an inverse. Now here, when we're talking about invertible, when we talk about functions in calculus, invertible means that the given domain has an inverse function where its domain is the range of this function. Now, if you go into linear algebra, having an inverse, it has to be satisfied for all the values in the domain. This is a slight difference, and we'll talk about that difference later. But for now, the idea is that we have an inverse if for every element in our domain, this cancellation property holds. And remember, just as a remark, we're going to reflect on the fact that the ln of x is the inverse of e to the x. Now, how do we compute the inverses? So suppose it has an inverse. There are two techniques that we will discuss. One, algebraic manipulation, and two, reflecting about the graph, or reflecting the graph about the x equals y line. Now, to compute the inverse using algebraic manipulation, we write down the initial function, isolate for x, switch x and y, and the result is f inverse of x equals y which is our new expression. So let's go through an example of doing this. So here we have f of x equals x cubed plus 1. So y equals 2x cubed plus 1. We want to get x by itself. So y minus 1 equals 2x cubed. Y minus 1 over 2 equals x cubed. And now here, we can take the cubed root. We're not introducing any domain restrictions. So y minus 1 over 2 equals x. Now we're going to swap our x and y's. So the cubed root of x minus 1 over 2 equals y. And now we get our f inverse of x is equal to the cubed root x minus 1 over 2. Computing this inverse is not a terribly challenging process as long as we know our steps. So I highly encourage you, go through these steps for the following functions and make sure you can compute the inverse of the function. Remember our steps, compute the inverse for these functions. Now, we have another technique we can use, and it is computing the inverse using reflecting about the x equals y line. Now, what does this mean? It means we simply draw the line y equals x, and we're going to reflect about this line. That gives us our inverse. And if I take the x equals line, y line here, my inverse is something like this. Okay. Now, notice that the inverse of the square root of x is x squared, but here we have a restricted domain. Our domain is x greater than 0. And here, if we flip along this x equals y line, and we reflect about that, what's our issue? Well, the issue is, what happens to our horizontal line test? It's not a function. This is what's called an inverse relation, but not an inverse function. Whereas for the x cubed function, we are able to flip it and still pass our horizontal line test. Now so this here does have an inverse, but this doesn't have an inverse. There are some functions like f of x equals 5 that will never have an inverse. Other functions can be made to have an inverse. And what do we mean by made to have an inverse? Is we introduce something called a domain restricted, or we look at restricted function. A restricted function is a function where the domain has been restricted. Now, why do we restrict functions? Many times we will restrict functions such that the inverse can be created for the function, given the restricted domain. We will explore two main examples of restricted functions in this course: sine of x and x squared. Or let's generalize sine of x to trigonometric functions. So our trigonometric functions will be our restricted functions, and x squared are our even powers. And here, we take sine of x, and we go from minus pi by 2 to pi by 2. We notice that we don't fail the horizontal line test. So this portion of the sine curve does have an inverse. And if we look at x squared and we just take everything positive and 0, that portion also passes the horizontal line test. So these two functions with the restricted domains do have an inverse. And we will explore that in greater detail shortly. And if you're taking A30, we will probably explore this within the first week of the course.